we're going to assume that this free electron that we're talking about is not bound, at least it's not bound tightly to the copper ion core, okay? So what does that mean? That means that I'm saying there's no restoring force. Let's treat it as if there is no restoring force. So that means that we're just going to say goodbye to this whole term here. But I'm going to add one additional term, right? And if we were doing a traditional problem of throwing a ball through the air or something like that, we might add this one term. It's a kind of a friction term, and it'll be opposite the direction of motion, so it'll also be minus. And I'm just going to call it gamma times dx dt. Okay?
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Lecture 107, Electric Current and Ohm's Law. So what I've drawn up here is a kind of a expanded view of like a wire, right? It would have cross-sectional area A and some length L, let's say, okay? And I've described the path that an electron might be taking through the wire if we apply an electric field in this direction. So this would be what would happen if we were to connect one end of the wire to a battery and the other end to the other end of the battery, right? So if we apply a potential difference across here, right? Just simply take that potential difference, divide it by the distance, and you get the electric field that you're going to get, the number of volts per meter across the wire, okay? That's going to cause the electrons in the wire to travel in the direction of the electric field, yes? But there's lots of stuff to bump into, and so it's going to be a bumpy ride along the way, and it's going to kind of bounce all over the place. So it's not a straight shot that it's taking, right? It's going to zip over here and down there and back here and then over there and down there, right? But we can describe this in general as it traverses across this wire, right? We can kind of treat it as if it were traveling in a straight line with a velocity we'll call the drift velocity, v sub d, okay? So all of these random motions will kind of average out, right, to one constant drift velocity across the wire. Now, we'll get into more details on all of that in just a minute, but first, let's just describe what this is. So I said electric current. What is electric current? Well, it's symbolized with the letter I, uppercase I, okay? And that's going to be equal to delta Q over delta T. So if I monitor a region in space, like say this volume here that I've drawn, and I calculate the amount of charge that moves through here in a unit time of delta T, that's the current, right? You can think of it as stuff flowing by, right? Electrons per second, right? If you saw 1 electron per second, that would be a current of 1 electron per second. This is going to be in coulombs per second, okay? 1 coulomb per second is called an ampere, named after Ampere. So let me just write the units of this. 1 amp equals 1 coulomb per second, okay? We can kind of calculate what's going on here, right? If we know what the electron density is in this material, right? That's the number of electrons per unit volume, right? Times the charge of each electron, we'll call it Q, so that's rho, the electron density, times the charge Q, times this drift velocity, then this will be equal to the electric current, right? So you take the density of electrons in here, times the charge of each one, times their velocity. I'm missing one more term I need the area, the cross-sectional area of the wire. The charge density times the number of coulombs per charge, right? Remember, this is going to be in amps per second. The area times the velocity. Remember, area has units of meters squared, right? And velocity has units of meters per second. So when I multiply velocity times an area, you can imagine an area moving, sweeping through with some velocity, right? That's going to sweep out a volume over time, yes? And if we multiply that volume times the charge density per volume, then we get the number of charges that we have in that volume, yes?
Yes.
Okay. So this is a definition for the current. It's just the charge density times the magnitude in coulombs of the charge carriers themselves, times the drift velocity, that's the speed of the charges, this average speed moving through here, times the cross-sectional area of the wire in question, okay? Now we're specifically going to be interested in talking about one material. You focus on copper. Copper is a really good conductor, okay? And so for that reason, we're going to talk mostly about copper today, okay? So let me put up some details about copper that'll be important. So the little information box I put up there is like an entry from the periodic table. The chemical symbol for copper is Cu. It has an atomic number of 29, which means it has 29 protons, and in a neutral atom, therefore, would have 29 electrons. The molar mass is 63.55 grams per mole. Okay? Its electronic structure, right? It has basically has an argon core, followed by 3d10 4s1. That's its outer electron shell, or shells in this case. So if we look at kind of a simple diagram of it, basically all the electrons shells are filled up except for this last one in which you have a single electron. Okay, that's in the 4s orbital. Okay, and what it behaves like is all of these electrons basically screen the nucleus. Okay, and so this outer shell electron all by itself here kind of behaves like a free electron. Okay, and we'll put that to practice a little bit later when we model this microscopically. But that electron, right, is you can treat it almost as if it's not even bound to this atom, right, because it's being screened by all of these electrons here. Does that make sense? That's kind of our simplistic model of it. So this is the charge carrier, this 4s1 electron. Okay? Does that make sense?
Yeah.
Okay. So let's calculate what the drift velocity will be. First, we need to get rho. Okay? So let's calculate the charge density here. We've got 1 electron per atom of copper. That's this 1 electron here, right?
Yeah.
Times Avogadro's number, 6.023 times 10 to the 23 atoms per mole. Right? Atoms and atoms cancel, right? Times 1 over 63.55. And this will be in moles per gram, right? 1 mole is 63.55 grams. Times, one more piece of information that we needed, right, was the density of copper. So its density is equal to 8.92 times 10 to the 6 grams per cubic meter. Okay, so I need to multiply times that density, so 8.92 times 10 to the 6 grams per meter cubed. Grams and grams cancel. And what do I get then? I get the density, rho. I guess I probably need to put in the, well, we'll just write it like this. If we multiply all this through, we'll get 8.46 times 10 to the 28 electrons per meter cubed. Okay? That's right, I left the charge out of that. Right?
Yeah.
So let's write that over here so we keep track of it. Okay, we know what the charge of an electron is. It's 1.6 times 10 to the minus 19 coulombs. And the area, we need to assume something for the area. So 12 gauge wire, we'll assume this is a 12 gauge wire. 12 GA, I think. And that is a wire that has a radius of 0.001. I think it's 0.26 meters. But it's really close to a millimeter, right? That's why I chose the 12 gauge. So we'll approximate it as 0.001 meters. That's a millimeter, okay? That's going to be the radius of this. So what I want to do is I want to solve for the drift velocity here, okay? So I'm going to write it over here because it'll be something we want to carry with us later. V sub d is equal to I, the current, divided by rho Q A. So let's plug this in. So we're going to have the current, we'll assume a current of 1 amp, okay? That's 1 coulomb per second. So we'll put 1 amp. And then we're going to divide by rho, which is this 8.46 times 10 to the 28 electrons per cubic meter, times the charge, which is 1.6 times 10 to the minus 19 coulombs, and times the area. And so the area of this, right, it's just going to the cross-sectional area, right? So that's the area of a circle. That's just pi r squared. So it'll be 0.001 squared, so it should be, so we'll just call it pi times 10 to the minus 6, and that'll be in meters squared. And so if we punch that into a calculator, we should get 2.35 times 10 to the minus 5 meters per second. That's about 2 times 10 to the minus, what is that, 0.0002 centimeters per second. All right, so is that a fast speed or a slow speed, you think?
That sounds slow.
So 0.0002 centimeters every second, right? That's pretty slow, right? That's like a snail's pace. Is that surprising? It should be, right? Because wouldn't you figure that electrons are probably pretty fast-moving things?
Yes.
So in the homework, one of the problems I gave you is to consider the electron orbiting in the Bohr model, right?
Yeah.
And to calculate what the period of that orbit is, how long it takes for the electron to make one revolution around, okay? Well, actually, no, what I ask you to do is to figure out what the speed is of the electron as it zips around the nucleus of a hydrogen atom. And so you do that calculation, you'll get a number. It's going to be on the order of like 10 to the 6 meters per second, right? Now, from thermodynamics, we haven't done thermodynamics or statistical mechanics yet, so I'm not going to really explain much about the formula, but there is a general formula, and it's called the RMS speed. Right? There are lots of different types of averages one can do, okay? This is the root mean square average. And in thermodynamics, we'll learn that 3kT, where this is not the Coulomb constant, this K is called Boltzmann constant, so usually it's K sub B maybe. And it converts a temperature into energy, okay? Divided by the mass of the electron. This is the root mean squared, right? That's the kind of, you can think of it as the average speed of electrons, well, of material, okay? It's a little bit improper to treat electrons this way, but if we do, right, then the root mean squared would be given to us at, say, 300 Kelvin. Is that the temperature I calculated it for? Yeah. If we calculate this at 300 Kelvin, which is roughly room temperature, we have 3 times 1.38 times 10 to the minus 33 joules per Kelvin times 300 Kelvin divided by the mass of the electron, with a 9.11 times 10 to the minus 31 kilograms. And if we run that through the calculator and take the square root, we'll get 1.17 times 10 to the 6, right? No, 5. 10 to the 5 meters per second. That's like 10 or 11 orders of magnitude difference, right? That's huge, right? It's like 10 billion times slower than the average thermal speed. This would be the speed due to thermal motion, right? Does that make sense? Now again, normally you wouldn't treat electrons this way. But if it was a gas, you absolutely would, okay? So you see it's moving much, much faster, yes?
Yeah.
Than what this drift velocity that we calculated is, okay?
Yeah.
So we'll try to get to the bottom of that a little bit, okay? By next considering a microscopic model for this current. So let's, but first I want to address the drift velocity thing one more time. So what's the difference here, right? So if we're going really, really fast, right? Why is this drift velocity so slow? And remember, there's an electric field that's applied here, right? So there's an acceleration, right? Because the force on an electron is Q times E, the charge of an electron times the electric field. That's a force. That means there's an acceleration, right? So why isn't the current like always increasing or something, right?
Yeah.
So, and this is my best explanation for that. So let me just make a note of these drift velocity, and we get that this for copper. But so to get an idea of the drift velocity, imagine a roadway, okay? And every so often there's a stop sign such that, let's see, your velocity looks something like this. Well, we would never have negative velocity, so let's just call this the 0. It means we can put the stop signs here. Car constantly accelerating at maximum acceleration, then braking, right, to stop at the next stop sign, okay? And if I all right, so here's the scenario, right? we're constantly speeding up and then slamming on the brakes to stop at the stop sign. So it's stop, go, right? And so I've broken up the interval between the stop signs into an acceleration period where you have positive acceleration and a period where you have negative acceleration. That's the braking. You're negatively accelerating, so you stop at the stop sign, you see?
Yeah.
And then you accelerate again, then you slow down by braking, speed up, slow down, you see? So your average acceleration, if you look at it, right, since when I'm speeding up, I have a positive acceleration. When I'm slowing down, I have a negative acceleration, right? So it averages out to 0, right? The velocity, on the other hand, right, I'm always moving in the same direction, yes?
Yeah.
And so if I average this zigzag velocity, right, where this is where I'm getting faster, and then I start to slow down to stop at the stop sign, you see? And then I get faster, and then I start slowing down to stop at the stop sign, right? The average velocity is somewhere in the middle here, right? And this is our drift velocity. Even though we were constantly accelerating, right, if we look over many such intervals, right, then we can see how even in the presence of an acceleration, right, we can still experience a constant velocity as it moves through the material, okay?
Yeah.
And it turns out that, these accelerations will mostly be from collisions with ions, right, the lattice in the metal. And that the acceleration due to the electric field is actually kind of small and negligible. But it does have this net effect, though, of this drift that we get across the wire. The stop signs, by the way, would be the ions. That's another parameter that we should introduce here. Right? This has a lattice parameter. What should we call it? I'll just call it a lattice constant. 3.615 angstroms. So that's every 3.615 angstroms, you'll get another copper atom site in the metal. Okay? So that's the distance between copper atoms in the metal copper. Okay? Because it's a solid, right? It's in a condensed state, right? It's not like a gas or a liquid where it's always moving around. So you've got these copper, right, which is surrounded by all these electrons, right? And so the electrons, the conduction electrons, or free electrons, are actually scattering off of these copper atoms that we see through there, okay? And we'll see them once every, 3.615 angstroms. So that's the idea there. I think I don't remember if I made a homework problem that deals with this. One homework problem I did put in, though, is what I call the raindrop problem, okay? And that is, if you're in the rain, and you've got to get from point A to point B, so that means you've got to move, right? You can't just stand there. What is the effect of walking or running, right, when you're running in the rain? And so I'll ask you to break that down and analyze it. And there seems to be, people seem to disagree on this, and so that's why I put the problem in there, okay? I think I put in a hint that makes it where you can actually solve it, but it's all related to this to this kind of stuff, okay? Now we'll do the microscopic view. If there was no metal there, let's say it was a total vacuum, and we had, the free electrons, right, that are due to this copper atom, present at some uniform density inside a vacuum, and I apply an electric field, right, those electrons are going to accelerate in the direction of the electric field, right?
Yeah.
Yeah, they're moving, right? So before, we've been talking about electrostatics. This is technically electrodynamics. Things are moving now, okay? And they're moving because I'm putting free electrons in an electric field that's accelerating them, okay? Does that make sense?
Yeah.
What about you? Now, before we've used this model, right, for an atom, a simple model, right? So we're going to use Newton's second law. We're going to write F equals ma, right? And so, let's see, F equals, let me write it like this because I always like to put the external forces on the other side. I'm going to write ma equals F, right? That's what we're writing here. So ma, well, that's just mass times d2x over dt squared. That's a second derivative with respect to position. And we would put in, we're going to have an electric field, right? So we'll have Q times E. That's a force, right, of an electric field on a charge Q. Remember, this is one single electron that we're modeling here. I'm going to put in a new force that we haven't considered before in our little oscillator model. Normally we would put in, I'm just going to write it over here to the side, this minus m omega naught squared x. That's our spring constant, right? This is K. It says that there's a balance between the electric field, right, that's pulling on the charge, and the restoring force that's from the ion center, right? So I'm assuming the ion is clamped in place, and this electron is free to move, right? It's being pulled by the electric field because it's being accelerated, yes?
Yeah.
But it's being pulled back on by the restoring force of the atom, right? That's the spring, right? So this was the old, you've got a spring attached to this, right? And so you've got this is the QE term, right? Pulling this way, and then we have pulling back this minus m omega naught squared x term, right? Where x is the displacement from its equilibrium position, right? Yeah, right? So that's that restoring force. But I said that we're going to assume that this free electron that we're talking about is not bound, at least it's not bound tightly to the copper ion core, okay?
Okay.
So what does that mean? That means I'm saying there's no restoring force. Let's treat it as if there is no restoring force, okay? So that means that we're just going to say goodbye to this whole term here. But I am going to add one additional term, right? And if we were doing a traditional problem of throwing a ball through the air or something like that, we might add this one term. It's a kind of a friction term or a viscosity. That's another term. Viscosity term. It's a drag, right? And it'll be opposite the direction of motion, so it'll also be minus. And I'm just going to call it gamma times dx dt. Okay? So that is a force which is opposite the direction of motion and is proportional to the velocity, right? So let me just rewrite dx dt is just velocity, right? Because that's what it is. Yeah? I'm going to rewrite d2x dt squared as the derivative of the velocity with respect to time. You see that?
Yeah.
Okay? Yeah, so here we have, by the way, this would be called a differential equation, right? And we're not going to solve it or go into the details of how to solve differential equations, but it just means that you've got a formula that involves a derivative and things that you're taking the derivative of, okay? It's not a hard one, but it is a differential equation. If I were to solve this differential equation, I think I'll put this in the homework too, right? Just because you guys, you're doing calculus, right? You know how to take derivatives.
Yeah.
So if I tell you that the solution to this problem, right, is that the velocity, if I solve for v, the velocity as a function of time is going to be equal to q, that's the charge of the electron, over this term gamma, times the electric field, times 1 minus e to the power minus gamma over m times t. Okay? If you solve this differential equation, this is the value you will get. Okay? So this will be your solution. All right?
Okay.
So in the homework, I will ask you, what you can do is you can take the derivative of this, okay? Multiply it times mass, right? And you can basically show that this solution satisfies this.
All right.
But I think I want to, well, we're going to replace a few things here because we can simplify it just a bit. But this is the general solution, okay? And the reason the general solution is useful is because of this exponential decay that I get over here. And I'll talk more about that in a second. But first, what we're really interested in here, though, right? This is a constant electric field, right? I'm interested in the electrostatic situation where there is no acceleration, right? We're going to assume the drift velocity, it's all constant now, okay? So you could call this the steady state solution, okay? It's what would happen after you start accelerating this stuff and it gets going, it comes up to speed, and then like if I had a ball and I threw it in the air, this would be ignoring the accelerating part. It would get to the point where it's falling now through the air at terminal velocity, okay? So if I drop a ball out of an airplane, yes, it accelerates every second, but at some point the drag force completely balances out the gravitational force, and we fall at a constant velocity called the terminal velocity, okay? So I want to look at the case where the change in velocity with respect to time is zero, right? This is the kind of the velocity is no longer changing term, okay? And if I do that, then that means that my velocity is now equal to, is that what I want to solve for? Velocity? Yeah, velocity. Velocity, which we're going to call the drift velocity, okay? V sub d will be equal to q e over gamma, okay? Does that make sense? All I did is I said if this left side is zero, if the change in velocity with respect to time, if the velocity is constant, the derivative of it with respect to time is zero, right? So this is zero. That means that this equals this, and then solve for the velocity v, okay?
All right.
Make sense?
Yeah.
Yeah. So we can identify this as the drift velocity. Now why do I want this in here? Well, because if I look at the solution here, this term gamma over m, I can rewrite this. If I let tau, we'll call tau the relaxation time, okay? If I let that be equal to m over gamma, then I can change this to e to the minus t over tau. So this is a typical parameter, right, that describes a decay, okay? And we call this time tau the relaxation time, right?
Yeah.
Now I want to think about it in my mind as if it's like what we'll call the, so if we think about the electron moving through this copper wire, right, and it's constantly banging into stuff, right, there's some time period, some statistical time period on average, right, that it's traveling before it bumps into something, right? Does that make sense?
Yes.
If it was, much denser substance, we'd bump into stuff much more often. If we're moving faster, we'll bump into stuff more often, right?
Yeah.
Does that make sense?
Yes.
And so we can describe this kind of this characteristic time as the time between collisions, okay?
Okay.
And that's going to be related to a distance, right? Well, what's the average distance that you can travel before you bump into something? That's called the mean free path, okay? Yeah, so I want to use this relaxation time, which has to do with this decay here, and then I can replace this gamma with, so if tau is equal to m over gamma, that means that gamma is equal to m over tau, right? So I can rewrite this solution as, and put the tau up here. Yeah? That's all I did, right?
Yeah.
And I can replace this gamma here. I can just call it m over tau. Okay? And so why did I do that? Well, if I were to graph this, right, this v of t, if I were to make a graph of it, okay, here's time, right? We will find there will be some point, we'll call this v sub d, the drift velocity. This line here is the drift velocity. And what we'll find is that depending on what tau is, as it goes from zero velocity, right, because we're saying that v of t is equal to 0, okay? And you can confirm that. Plug in t equals 0 in here, we get 1 minus 1 is 0, right? So we've kind of we're forced to adopt that notion if we want anyway, the velocity at t equals 0 is 0. And so what will happen is after it bumps into something, it starts speeding up again, and there's going to be some characteristic time before it makes a collision, and then eventually equilibrates to this drift velocity, you see? So this would be for, 1 tau. If I choose a larger value of tau, right, what would that entail? That would mean that either my mass was much bigger, or this viscous term, which was in our original equation, gamma, would be much smaller. If that was the case, then this would more slowly, well, that's a terrible drawing of it, be much more slowly in its rise up to the drift velocity position. That's where it equilibrates to, right? If enough time has passed, right, then we will be at this drift velocity, okay? When we say that dv dt is 0, we're saying we're well past this point, we're already traveling at the drift velocity. Okay, but I want to consider the general solution so that I can get this idea of this relaxation parameter, right, tau, that I can put in there. And I'm going to, note that we're going to think of that as like the time between interactions, okay? But it's a relaxation parameter, okay, that has to do with the decay of this exponential right here, okay?
Yeah.
All right, so we put that in. What are we going to do with it now? Well, we have an expression for the drift velocity here, don't we? But we had an expression from before for the drift velocity when we considered it kind of phenomenologically as a current through a wire, right?
Yes.
So why not put the two together, right? If they're supposed to be the same thing, let's see what the consequences are if we simply equate this with this, okay? So if we do that, I don't need this anymore. I do want to make a note that, well, that's fine. We don't need it. We'll be good. And we don't need this. What we do need is this. So I've got this equals this, right? So that would say that I over rho QA is equal to tau QE over M. Okay? So we can rewrite this as I is equal to, I've got tau, I've got Q, I've got rho, I got another Q, that's Q squared, rho Q, got that. I'm going to keep the A over here, the area from here, and then we have over M there, yes?
Yeah.
It's looking good, so, and we still have E to deal with, but let's remember, right, that the potential, right, is defined as the line integral of E dot dl, which in a simple wire case, right, we can think of as just a simple product, right? So if it's just a wire, right, it's just E times L, length of the wire, okay? So if I want, I can solve for E, that's just V over L. So I'm going to put this L down here, and I have my V, my voltage, right? Yeah? Put it right there. Now it's starting to look interesting, huh? Because, does anyone know Ohm's law? Who knows Ohm's law? Well, I know it. Anyone remember Ohm's law? I think no, I don't know if we've ever talked about it before, but you might have run into it. Ohm's law says that V equals IR. That's how people remember it. V equals IR, Ohm's law, right? I'll write it up here. V equals I'm going to write it RI, okay? Another way you could say that is I equals V over R, or I equals 1 over R times V. You see where I'm going with this?
Yes.
Yeah? In your homework, you'll explore a problem where you attack this from a different perspective, okay? And you'll come across your first attempt at it. You'll notice that, well, that's funny. I'm getting something where the voltage is related to the current through the square root of the field, right? Or the current is related to the square root of the field, so the square root of the voltage. And that's, seems wrong. You have to make some course corrections, and then you'll get eventually that you can find that the current is proportional to the voltage and not the square root of the voltage. But here we've got something, right? And so we have basically Ohm's law right here, okay? Typically this portion of it here, this is called the conductivity. It's usually denoted with sigma, okay? This A and this L, these are values that have to do with the physical parameters of the wire, right? The cross-sectional area of the wire, the length of the wire, right? So they want to have a constant that really only has to do with the fundamental stuff, right? This mean free, this time between interactions, the charge of the square of the charge carriers, the density of the charge carriers, the mass of the charge carriers, right? They want all those physical things separated from these other geometric aspects of the problem, the cross-sectional area of the wire and the length, so that they can make tables and so that you can look these things up. Okay, and we're going to look something up here in just a minute. But just this is called the conductivity. Conductivity. Related to it is rho. I know we have a lot of rhos, okay? But it's just what people use. They use rho to be the resistivity. Kind of regret using rho for charge density now, but that's fine. We're not going to use this much. And they're related, right, that sigma is equal to 1 over rho. They're just inverses of each other, okay? So 1 over the conductivity is the resistivity, and 1 over the resistivity is the conductivity, etc., okay? But the R in what most people think of as Ohm's law, right, this is big R, and this is equal to rho, the resistivity, times L divided by A, okay? And so what you'll do is you'll look up in a table, resistivity has units of ohm meters. And I didn't even say what an ohm was, did I? An ohm, it's right over here, 1 ohm is equal to 1 volt per amp. So we can look up a value in a table, right, for say copper, right? That will give us this resistivity, right, which we can then plug in. And then based on the wire, like the length of the wire that we're using and the cross-sectional area of the wire, right, we can calculate what the resistance is for that wire, okay? And we'll do that now. We'll do an example, okay? Let's get some of this out of the way. We'll probably want to keep this around. We don't need that since it's all kind of built in there. There we go. So let's see what we can do here. Let's calculate the electric field for a 12-gauge wire, since we already dealt with a 12-gauge wire, for carrying 1 amp of current, okay? So let's figure out what the electric field is for that. So, and the data we need to look up, right, is that the resistivity of copper, I'll write it as like this. That makes it a little nicer, so we don't have to mix it up with our charge density rho that we used before. Where's my number? It's 1.7 times 10 to the minus 8, yeah, ohm meters. Okay? And we're still using that 12-gauge wire, right? So that's a millimeter radius, right? It doesn't really matter what length we use. It's going to cancel out in the end, but we'll say we're going to use 1 meter of wire. So we can calculate what R is. R is going to be equal to this number, 1.7 times 10 to the minus 8 ohm meters times length over area, right? Length over area. We'll say 1 meter. And the area is going to be that pi times 10 to the minus 6 meters squared, right? And so that's going to give us, in the end, a resistance of 5.4 times 10 to the minus 5. No, minus 2, or minus 3 ohms. Okay? So there's our R value. Okay, so that's the resistance that we would have, right? So we can then use Ohm's law, right? V equals IR. We said this is for a 1 amp current, and we know what the resistance is, so we know what the voltage drop is. But so we plug this in, we'll get 1 amp times this 5.4 times 10 to the minus 3 ohms. That's going to give me that V is equal to 5.4 times 10 to the minus 3 volts. Okay? Make sense? And so the electric field then, which is just equal to the voltage drop divided by the distance, right? Since our distance is 1 meter, right, this is going to be 5.4 times 10 to the minus 3 volts per meter for the electric field. Okay? Let's try and estimate what the time between interactions is, okay? The tau that we had up here, right? So if we use, do I have it written here? The drift velocity is equal to QE times tau divided by m. Then I can see that tau is going to be equal to m times the drift velocity divided by Q times E. We're going to use the drift velocity that we calculated earlier, which we got 2.35 times 10 to the minus 5 meters per second, remember? And then m is the mass of the electron, so I have 9.11 times 10 to the minus 31 kilograms, times the drift velocity, 2.35 times 10 to the minus 5 meters per second, divided by 1.6 times 10 to the minus 19 coulombs, times the electric field that we just calculated here, 5.4 times 10 to the minus 3 volts per meter. So we got that. We can get this out of the way, yes? And what do we get for this time? If we run this through the calculator, we should find that this is equal to about 2.5 times 10 to the minus 14 seconds. Okay? So that's the time in between interactions. If we assume that the mean velocity, right, is equal to the RMS velocity that we calculated before in terms of thermal motion, right? If we treated electrons as a gas at a temperature of 300 Kelvin, then that was about 10 to the 5 meters per second, right? So if we assume that's the speed, 10 to the 5 meters per second, then we can use the relationship that this average velocity is equal to the mean free path. Usually they use lambda for that, okay? Divided by this time between interactions, okay? It's kind of the definition of that average, okay? And we can solve for lambda here, right? So it's just going to be this mean free path is equal to this velocity, 10 to the 5 meters per second, times tau, this time between collisions, which is 2.5 times 10 to the minus 14 seconds, and that's going to be, well, minus 14 and 5, right, that's going to be minus 9, so this is 2.5 times 10 to the minus 9 meters, which is 2.5 nanometers, okay? Remember before I said that the lattice spacing was 3.615, where'd it go? 3.615 angstroms, right? So if I take the 2.5 nanometers, that's the distance that the electron travels before collision again, right? And I divide that by this 3.615 angstroms, this can tell me how many lattice sites it's passed through, right? And that's going to be on the order of about 7 or so lattice sites. So the electron is whizzing past about 7 lattice sites in the copper metal before colliding with one of the ion cores, on average, okay? And that's all I got on that. So we derived Ohm's law, okay? It had the right dependence. the current was proportional to the potential energy. The current was proportional to the potential. Okay, the voltage, right? And we got some constants that had parameters that made sense in terms of what causes resistance in wires, right? So it's bumping into the ions, right? The problem is much more complicated than we laid it out to be, right? Because the ions, they're vibrating, and electrons are not really like a gas. You really need to treat them quantum mechanically, and then they would then be treated more like a wave, okay? Even the lattices that we considered, which were like perfect in our minds, right? We just had a single lattice parameter to characterize it. That means it's periodic, that every 3.615 angstroms we encounter another copper ion core. If we treated that quantum mechanically, perfect lattice, you'd have a superconductor, right? There'd be zero resistance to it. But as you can see, with the calculation we did do, right, the voltage drop right across 1 meter of copper wire was teeny tiny. It's insignificant, right? So there's not a whole lot of resistance in a good conductor anyways. But this is Ohm's law, right? If we just simply rewrite this, we get V equals, now we just invert everything, right? M over tau Q squared rho times L over A. This is all R, resistance, times I, the current, right? So V equals I times R. That's Ohm's law. Okay? We'll use Ohm's law next time when we talk about Kirchhoff's rules and analyzing DC circuits. Okay? Any questions? That's it.